That finite means that there is a positive number epsilon which is in the place of R in the definition, and finite means which is totally bound. So it is complete and totally bound. This side is easy. The other side is we need to prove that now, assume that the space X is complete and totally bound. And we need to prove that it's compact. So suppose that X is it's totally bound. Complete and totally bound. So we want to have a sequence which has a convergent subsequence. X is assumed to be totally bound. So there is this covered by open walls of finite covered by open walls of finite radius. So let us take one of these open walls, and then we let the set where S1 is the indices of the sequence, where the sequence actually belongs to this ball. So if any member of the sequence belongs to this ball, then we put its index into the set S1. And then we construct inductively these sets S sub n. So let S sub k be equal to this. So we have for each natural number k, D sub k is the open ball with radius 1 over k, which is a positive number that contains infinite subsequence of that. Oh, actually, we need to have infinite subsequence. So infinite subsequence. If it is finitely many balls which is covering this space, so that infinite sequence will at least there will be one ball which has infinitely many of them. If all others contain only finitely many, it doesn't matter. At least one will contain infinite member of that sequence, right? So we're taking that one for S sub k, for each k, so that it has infinitely many members in it. So for every k, natural number k, this S k is a finite infinite subset of, it is an infinite subset of natural numbers, because it consists of indices of these infinite sets. And for every different indices, not necessarily different, every indices x, I, j, so that this n sub I, n sub j belongs to sk, and which has radius 1 over k, which means now this is a Cauchy sequence.
How should we fix our radius 1 over k?
Pardon?
We should fix radius 1 over k, but how we get this one?
How do we get this one?
Yeah.
This which one?
Radius 1 over k.
Oh, 1 over k.
Yeah.
1 over k, we just make it
Smaller.
yeah, just a positive real number epsilon. In which place we put 1 over k, 1 over a natural number. This is actually done by all the intuitionist mathematicians all the time. They never use epsilon. They use 1 over n all the time, so that we can construct it even using compass and ruler. So that was what they. So the 1 over k is a positive real number we get to be reduced, because we said that 1 over k. You see, if we said that bk has radius 1 over k, right? bk has radius 1 over k, therefore any 2 points in this ball will be of distance both 2 over k, which is our epsilon. Probably that is where maybe we should use 2 over k here. In the low xi, xj smaller than equal to 2 over k. It's fine. Yeah. Thank you for the comment. I think you are understanding this. So that we prove that it is sequentially compact. Sequentially compact means that we have an infinite subsequence which is convergent. We have an infinite subsequence which is Cauchy. Is that right? Have a look at that. This is not what we wanted to prove. Because we are not assuming, we are assuming that it's complete right now. Can we
Yes.
go back to the beginning of the second? We are assuming that it's complete right it's complete. Okay.
Yes, sir.
Yeah.
So now it's fine. So it's totally bounded and complete. So that's this is everywhere on the internet. These things are one of my colleagues from Pakistan asked complained to me that she wanted to form exercise question set for a course. And every time she checked online, the question is online and the answer is online. She wanted to have questions, some of the questions which you cannot find the question online or the answer online. And I told her that I can give you any number of such questions, but we cannot really do this in Facebook Messenger because I can't write nicely on that. Even talking is not good enough. So if she comes, we can actually give for lots of questions. For example, we will see lots of such questions in this course, so don't worry. This one is everywhere on the internet, so you can find it on other groups as well. What time is now? We will use only 90 minutes. 30 minutes, continue. So we prove that the matrix space is compact if and only if it is, yeah, go to L2. It is it is complete and totally bounded. This, you need to really realize that this, you can do an exercise question saying that you can prove it that this statement, complete and totally finite, is equivalent to the subset, the set being closed and bounded. Because in topology we prove compactness to be that compact space. So we now go into these first 2 or 3 batches of slides are completely known mathematics. We include it because we're going to rely on them all the time. So we now consider in mathematics there is some sort of something like this martial art prescription or recipe. Martial art recipe that we define a new concept, the mathematicians define a new concept. The next natural thing to do is look at sub-concept, sub-object, definition of a new object, and look at what sub-objects. Then we look at mappings between of this type of objects. Now we're going to the third step where we look at mappings between metric spaces with their respective distance functions. So X is a metric space with distance function rho sub X, and Y is a metric space with distance function rho sub Y. So far nobody asked me about this rho. Many people, even it's sunny out here, even in this, your student uses D for the distance. And many English people really insist on that, and I really object to it. My objection usually has 3 good reasons. I use rho for the distance, which comes from R actually. Rho is the letter R in Greek. I don't use D because we are also using small d to be the diameter of a metric space. If we use same symbol both 3 times on the same slide and give the respective definition, that is not an abuse. But if you use this D for 5 different things in the course, then it will confuse the student and it is called abuse. Abuse of symbol means that you use it at least 4 times for 4 different concepts. In mathematics, we can actually tolerate up to 3. So I don't use D because rho is free for me, and no other occasion where I'm using rho. And classical text always, second reason is classical text always uses rho. Function analysis, classical. So now 2 metric spaces, not necessarily 2, it could be y is equal to x, but x, y metric spaces with their respective distance functions. and f be a mapping from x to y. If it is bijective and preserved distance, then we call it isometry. Or if it is a mapping which preserved distance, we call it distance preserved. In group theory, we define homomorphism, it preserves products. Image of product is product of the respective images. In topology, continuous mapping is inverse image of an open set is open. The open set is a crucial thing for topological spaces in modern mathematics. In graph theory, we define homomorphism so that image of edges are edges. So this is one very natural mapping, mapping which preserves distances, because in metric space we only have distances. If we preserve distances, we call distance preserving, and if it is bijective, then we call isolation. So we get an easy thing here. If a mapping preserves distances, if these 2 points have the distance, the image has the same distance, then we can actually easily verify that it's injective mapping. It's an injective mapping. In fact, it's the metric space X is isometrically embedded into the metric space Y, where the mapping which we are now considering F restricted on X becomes an identity mapping, which is actually isometry now. Isometry is defined to be bijective distance preserving mapping. So this can be easily proved. I think if you prove this there, we'll skip it, we should go through it. Proof is there, it's not difficult. Using the distance axiom, how do we prove it? Because in school, teachers teach us injective mapping. The original definition of injective mapping is if x1 is not equal to x2, then fx1 is not equal to fx2. So many people use one-to-one, which I don't like. Because they use this word one-to-one for both injective and bijective in the same book sometimes, which I don't like. Injective is very clear because there is another reason. One-to-one cannot be put into noun, verb, and adjective. An adverb. I can change this word into injection as noun, injective as adjective, injectively as adverb, inject as even verb. So I have freedom, I have advantage of using all different word classes when I need. If you say one-to-one, it's all one-to-one. Now noun is one-to-one, adjective is one-to-one. Completely confusing. If x1 is not equal to x2, implies that fx1 not equal to fx2. Its contraposition, the word contraposition is also the word I really complain about. Contraposition is a Latin word. Contra means against in Latin, right? Position means put there. It says put against. Contraposition in ordinary English, put against. Still, it's got completely confused English. Because contraposition ought to have been, De Morgan was the one to blame. De Morgan was English mathematician who used this word first, right? And then he is English and he put it down and we have to follow. It's not right. It has to be negative converse or converse negative is much better. The converse of the negative or negative of the converse. That is the contraposition. If A then B then, if not B then not A is what we're talking about. This is, if you negate this one, school teachers really fond of teaching us this. Equate the two function values and then try to solve and get x1 equal to x2. Isn't that what she said? Yeah. That is what is this cylinder here. It's a negative of the converse, and that is used using the axiom number 1. Next. Yes. This is in a very broad generality. If you have any category of mathematical objects, for example, groups, all the automorphisms of a group forms a group as well.
Yes, yes.
All the linear automorphism of a vector space forms a group as well, which is called the general linear GLV. GL and V, if the dimension is n. For graphs, for any given finite undirected graph, not necessarily connected, for any finite undirected graph, its automorphisms form a group. Its proof is also like this, very simple. So for metric spaces, our crucial thing is isometries, which is bijective mapping that preserves distances. This forms a group. Proof is very easy. It's here. So I think you should read this. Let me go through this slowly. So we want to prove that composition of 2 isometries is an isometry, number 1. Number 2 is it is associative. The composition is associative. Number 3 is identity mapping is an isometry. Number 4 is 3 group axioms. Number 4 is every mapping has an inverse, which is also an isometry. And this is what we prove. So first we prove that if FG are isometries, then FG composition is an isometry because FGX, FGY have distance equal to distance of GX and GY, which is because G is an isometry, so which is the same as this distance is equal to distance between X and Y. So this belongs to the composition belongs to the set. Similarly, you can prove that. You don't need to prove the associativity because any mapping from a set to itself, not necessarily bijective or even injective, any mapping from set of all mappings from a set to itself, composition is true. That is proved usually by a commutative diagram. When I was teaching linear algebra many years ago, I taught many years in linear algebra. I asked the students to prove that product of 2 n by n matrices, invertible matrices, invertible matrices. What did they do? Many of them did expand it out by taking this row, this column, multiply, that row, that column, multiply, and then wrote 2 A4 pages and proved it. It's a bottom line proof, and you have to give full mark. FGHR mappings from X to X. This diagram is commutative, so this arrow gives you GF. Right? GF composed with H gives you that. This one is GF composed with H. Look at it another way. Look at it. We need to look at this one first. This one. This arrow. This arrow is HG.
Yes.
And if you compose it with F, you get that. Because this is the same arrow, so these two are equal. That is all we need to do for any mappings from a set to itself. It is even if it is not could be a monoid. It is a monoid, but even if it is not a group, the associativity is true. Therefore, isometrics being bijective mappings, they are mappings, and therefore associative. And identity is obviously isometric. Identity mapping, mass x to x and y to y. So the distance to the x and y, distance to the x and y. And it is bijective, therefore it's invertible. And you look at the condition for isometry, then distance is preserved backwards. So we have, this is the group. Before we work, time is up, right? Let me ask you a very general question. I think you should write it down. It's not in my lecture note. Given any metric space, let X be any metric space, determine the group isom X. Anybody knows this question is completely solved in general? Thank you very much. See you tomorrow. Day after tomorrow. Okay. Tomorrow, what is the activity of this hour?
Do we have classes tomorrow at this time? The class है और वो
नहीं इस टाइम कुछ नहीं है
It is very this time. Is it possible to join this on tomorrow?
Yeah, we'll join it tomorrow.
Yes. That is fine.